Welcome to Emtron Training Part 40. In this training tutorial, we're going to be taking a look at working with our open loop style idle control. Open loop control integrates an idle control motor to give additional airflow and additional engine torque as needed. We'll find that we can utilize the open loop idle control for cold starting conditions or to offset something like a cooling fan turning on. If we turn air conditioning or power steering, anything that's going to have a draw on the engine and reduce the engine's torque, we'll use the airflow from the idle control motor to offset that lost torque. We have a lot of things to cover. Let's jump in so we can work with our open loop idle control. Okay, so let's get started. We're going to be taking a look at working with our open loop style idle control tuning within our Emtron ECU. Our last video, we looked at the basic idle control. We learned the fundamentals of how idle control works. We have a certain level of airflow coming into the engine. We have a certain amount of spark timing. The combination of both of them give a certain level of idle torque. Depending on what that idle torque's at, that's going to influence what the engine's going to idle at in terms of engine speed. We want to be specific of where we're allowing the engine to idle at. We don't want it to idle at 2,000 RPM. We don't want to idle at 400 or 500 RPM. We want to generally idle 900, 1,000 RPM on a warm idle for a majority of engines we're going to be calibrating and tuning. In order to achieve that, we can open up our throttle plate, allowing essentially all that fixed airflow to come in, and then use the spark timing to fine-tune the idle torque and the idle conditions. However, we're going to get into a situation on cold starts. The engine's not going to want to fire up cold. We have the viscosity of the oil thicker, creating more frictional drag on the engine. We'll also find that we have a wall wetting effect, where the atomization of the fuel spraying out of the fuel injector is poor, and we lose some engine torque. A combination of both of those, we'll lose maybe 3, 4, 5 pound-feet of torque out of the engine at idle and cause the engine to idle lower, because our idle speed is dictated by the engine's torque production in idle conditions. So we can utilize our idle control motor and we can bring in more airflow. More airflow means more idle torque, and therefore we'll idle at a higher RPM and offset that torque loss. We can use the idle control motor to help start up either warm or cold, getting the engine to fire up and run and hold at an appropriate RPM level. We also can use it to compensate for things turning on. A cooling fan turns on. Let's say the cooling fan has a relatively high amperage draw that draws down on the alternator pretty hard. The alternator starts charging more, and it's going to be pulling more of a drag on the engine, actually losing and reducing engine torque. We can offset that by adding more airflow through the idle control solenoid. So we're using the idle control solenoid in this open loop manner very specifically. I'm going to go through how I implement the open loop idle control in race engines that I'm calibrating and tuning. There are various different ways that you could work with this, but I found the most success going in and working with my specific way. Again, I'm going to share that a little bit later in the tutorial. The first thing we need to do is go in and actually turn on the idle control feature and learn about the different types of idle control motors you might be working with. There's pulse width modulated and there's an idle stepper, and there are going to be differences in terms of the control that we need to know about. Let's go and take a look at how to do that right now. So the first thing we're going to do here is jump up into configure, and we're going to move over here into functions and to function output setup. In function output setup, we're going to find here that we have a whole bunch of different things under engine functions that we can turn on. This is going to be, in particular, looking at the idle speed control for this tutorial. We want to turn this from off to on. Now, this is assuming you have an idle control motor fitted to your engine. If you're dealing with something like an older Honda engine, you're going to have a pulse width modulated style idle control solenoid. If you're dealing with something like a 1J or a 2JZ, you'll be finding you have a stepper style idle control solenoid. So we need to understand the differences and programming them. So let's jump in here real quick. Let's pop into our window. Let's turn this on, and then we'll start to break this down here. So the function type we see here, we have a whole bunch of different options. This is telling the Emtron what type of idle control solenoid we're dealing with. We have pulse width modulated or stepper. Now, they both achieve the exact same result, meaning they're bypassing a certain amount of airflow across the throttle plate. So if the throttle plate's open, it's fixed. Let's say it's pulling in 4 grams per second worth of airflow, but we need something like 6 or 8 grams per second worth of airflow to be able to get the engine to fire off cold, or just under cranking conditions to get the engine to fire off clean. That's where the idle control solenoid is going to come from and come into the picture here, where we're going to be introducing more airflow through the idle control solenoid, but we're going to go about it in 2 different ways. We have either, again, a pulse width modulated or a stepper, both achieving the exact same kind of results, just getting more airflow bypassed from the throttle plate. So in this case, we have a 2-wire and 3-wire solenoids. This designates a pulse width modulated style solenoid. Now a 2-wire solenoid, these are found on older Honda engines. So a B, D, or H series engine, they're going to be a 2-wire design, and 1 wire is going to be power. The other wire is going to be sending a pulsed signal to the solenoid. The more that we pulse it, the more it's going to have the duty cycle range. It's working in terms of duty cycle. So 0 to 100%, the more that we're pulsing and holding on the solenoid in its pulse width modulated output, the more airflow we're going to allow it to bypass. So 0% duty cycle means that we're sending no airflow through that solenoid. 100% duty cycle means that we're sending the maximum amount of airflow through that solenoid. Whatever the valve size is going to be is dictating how much airflow we can actually bypass. Essentially we can treat all of this like a controlled vacuum leak. So how much of a vacuum leak we're creating. So in a 2-wire solenoid, very basic circuit, pulse width modulated, typically always going to be a low side output in terms of the pulse width that we send out. We'll find if the solenoid was wired backwards, meaning we were grounding the solenoid, then we would have to send out a high side or a 12-volt pulse to the solenoid to activate it in terms of the duty cycle control. Let's just go here and click 2-wire. We're going to find that we have our idle speed control here where we need to go in. Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here, and you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.